Hi everyone, my name is Shilpa Kancharla and I'm an engineer on the Tensorflow team. In today's workshop, I'll be walking you through generative adversarial networks and stable diffusion. Let's go ahead and get started with GANs. Before we take a look at the structure and inner working of generative adversarial networks, let's discuss what they are. As the name suggests, generative models generate new data, while discriminative models work to differentiate between different data instances. And as shown on the example to the right, a discriminative model would work to draw a boundary between identifying two different data points, like is this a 1 or is this a 0? Meanwhile, a generative model groups together zeros or ones together and it tries to determine how data is placed throughout space. So in the context of GANs, a generator will attempt to learn how to generate plausible data while a discriminator tries to distinguish between real and fake data. And this figure can help illustrate this concept in more detail. Essentially, we have our generator on the left trying to create what looks like a real currency note. Its first attempt isn't that great, as you can see, and the second attempt is a little bit better, but also not that great. But as training progresses, it's finally able to generate what looks like a legitimate dollar bill. So as the generator tries to create plausible data, the discriminator evaluates what is real and what is fake data. After a certain amount of training, the discriminator will have a much harder time telling the two apart, that is between the generated and the actual data. And through that, the discriminator will ultimately fail and just have a harder time. And here's another representation or metaphor of the GAN structure. The generator is a neural network attempting to create pictures of cats. In a way, it's like an artist trying to perfect its work. And the discriminator acts as an art critic and tries to discern which pictures are a closer representation to cats than others. After a few attempts, the discriminator has a harder time determining which are real data points and which are generated. And in a generative adversarial network, both the generator and discriminator are neural networks. The generator output is connected to the discriminator output. And then through that, backpropagation occurs. It allows for the neural network to improve its accuracy. And specifically in GANs, the discriminator's classification provides a signal that the generator can use to update its weights and therefore produce more accurate predictions. And in summary, through discriminator training, the discriminator classifies both real data and fake data from the generator, and then the discriminator loss will penalize the discriminator for misclassifying a real instance as fake or a fake instance as real. And the discriminator also updates its weights through backpropagation from the loss and through the discriminator network. And then onto the generator, it also has backpropagation, but like we take the results from the generator loss and the discriminator loss, but here we're only updating the weights for the generator. And in summary, how this process works is that we sample some random noise, produce a generator output from the sampled random noise, and then get discriminator, like the real or fake classification from the output. And then you calculate the loss from the discriminator and then backpropagate both the discriminator and the generator to obtain the gradients. But in the end, even though we're using both of those weights, we're only updating the generator weights. And I'll talk a little bit about a really popular structure. It's called deep convolutional GANs. And we'll walk through a little bit about each of the features in it. And they're a popular network design based on the GANs architecture, and they're typically known to have pretty great success. Some key aspects about it are it replacing the max pooling with convolutional stride and also using transposed convolution for upsampling. And I'll explain transposed convolutions a little bit more. But before I do that, here's a quick review of convolutional computation. So essentially in convolution, we perform this element-wise multiplication between a section of the input image, which here has been translated into pixel values, and we take those values and multiply them by a filter. We take each of the values from the element-wise multiplication, you add them together to get that output or that result that you can see on the right. So in this case, we've multiplied 2 by 1, 0 by 0, 1 by 1, and so on and so forth. We add all those together and we get 3 in the end. And then we do this at each space in the output. We kind of slide that filter or slide the section that we're looking at over, multiply it by that filter again, and then we get that output result. And also an important thing to note here is that we are downsampling in convolution. This is a key distinction that will come up between convolutional operations and transposed convolutions, otherwise known as deconvolutions as well. And I'll explain those next. So before I kind of look at a worked example of transposed convolution, I wanted to real quickly introduce the Tensorflow Keras API. It's a lot like perhaps the Con2D layer that you've seen before. Basically, it's just Con2D transpose, and like Con2D, you pass in a parameter for the filter, the kernel size, the strides, padding, and if you want to initialize your kernel with some values, you can do that. And you add that as a layer to your neural network or deep learning architecture. And now we can kind of move on to talking about transposed convolutions or learned upsampling deconvolution. There's kind of 3 different names that you can use interchangeably for it. So here, an important thing to note is that the output size equals the stride multiplied by the input size. And at each step, the value of the input image is used to weight the filter, and the result is copied onto the output image. And so just in our example here, we see input image, just 1, 2, 3, 4, those are the pixel values, and the filter values, all of them are 1 at the moment, but these change as you do backpropagation, as in the other case, convolution as well. So let's start with the first value. So we take the 1 and we're essentially multiplying that value with the entire filter, right? So every place we'll get like 1 times 1, as shown as in the output image. And then if we move forward, this would be the next pixel, and then this is where it's placed on the output image. And here we're using padding same, so that's an important thing to note, which is why there is, even though there's not enough space at the end, it just gets added to those values. So we perform the next set of multiplications, and we know that 2 times 1 is 2 the entire time throughout, and then we essentially add those. So in the last slide, I showed that column was all 1s, and so now we add 2 to it to get 3, and then the column that didn't have any values before now has 2. So that's how transposed convolution is a little bit different than normal type of convolution, in that we are upsampling in this instance. And I'll quickly go over the training loop for deep convolutional GANs before I kind of walk through the code. Basically, here's the training loop for it, and we start by creating generated images in which noise is injected to them in the training mode. And then we run the real and fake inputs to the discriminator to generate the real and fake output. And then from there, we calculate the discriminator and generator loss. And then this is also part of the training loop. And then as you can see from here, we are calculating the gradients to update the weights of the generator and discriminator. And then to go more in depth, the discriminator loss compares how many predictions are correct. Like, as I've said before, how many instances are real that are actually real data versus like if this is fake, like, oh, obviously the generator created this. So it's, again, able to distinguish between real and fake images. And we can say real images, we can call them an array of ones, and then it compares the predictions on fake or generated images, which consists of an array of zeros. And then next, the generator loss compares how well it's able to trick the discriminator into thinking fake images are real. And then if the generator is performing well, the discriminator will be able to classify fake images as ones, even though, as I mentioned on the slide before, they're actually zeros. So with that being said, I think we can move on to the code walkthrough. So I'll give everyone a few seconds to type that URL in and look at the notebook if they're interested. We can go ahead and get started. So I will switch over to the other tab with the Colab notebook. Okay, so you should be able to see the notebook on DC GANs here. And we'll just be going through some aspects of it. You all might be familiar with the MNIST dataset. It's a dataset of handwritten digits. Traditionally, it's used for training. It's like kind of like the hello world of computer vision, in a sense that, can you train a CNN to correctly identify a handwritten digit, like as a 101? And so the following animation actually shows a bunch of images that were produced by a generator that was trained over, I believe, 50 epochs. And then the image starts with the random noise, but as training progresses, it develops into resembling handwritten digits over time. And this is just some of the basic setup steps. We're importing TensorFlow, and then to generate the GIFs here, we're using some basic helper libraries. And then we have the rest of our imports here. Yeah, we're mostly writing this in TensorFlow and Keras, so it's important to import those layers. And this is how you load and prepare the data set. So we're downloading the train images and train labels from the TensorFlow and Keras dataset API. So we'll go ahead and load those in, and then we can know that the shape of it is starting out as 28 by 28 by 1. And we also go ahead and normalize those images. And we batch and shuffle the data set. And an important thing to note here is that as we're creating these generator and discriminator models, or those loops to train them, we are using the Keras sequential API. And as I mentioned before, we're doing transposed convolution. So using that con2D transpose to do the upsampling is key here, as opposed to just the con2D layer in normal convolution. And we are basically creating the generator model here. We start with it by calling a sequential model, and then we're kind of adding each of the layers to it. We start by adding a dense layer, and then we use batch normalization, and then the activation function ReLU. And then from there, we're reshaping the model. And then we start doing the transposed convolution. And then another batch normalization and activation function. we add in that same block again. And then finally, we return the model at the end. This is our generator model. This is essentially again, the neural network that will learn to generate the images that will try to fool the discriminator. And then, interestingly enough, I think I mentioned in the beginning of this code walkthrough that the generator basically starts off by just producing noise. I think you can see it in this animation right here. Like at the very beginning, there's a blip of noise right there. So before we even train the generator, this is what the untrained generator produces. And then now we create the discriminator model. And it's just the discriminator model here is just a CNN-based image classifier. It's just going to tell us, is this real or fake? Is this a handwritten image or not? And then, yeah, so the model is basically trained to output positive values for real images and negative values for fake images. And then we go ahead and we define our loss and optimizers here. We're using binary cross entropy because this is a binary problem like real versus fake. And then from there, we write a function to calculate the discriminator loss. And again, it's cross entropy. This is where we have it defined here. So we basically take that and we're saying the real data is akin to an array of ones, while the fake data is akin to an array of zeros. And then we calculate the loss from there. And then we also write a custom function to calculate the generator loss. Basically, do the fake images get classified as reals? So do zeros get classified as ones? And then we use Atom as our optimizer. And then there's also this part here about saving your progress in training in case you need to come back to it. It's pretty useful, especially if it takes a long time to train your model. And then now we're just kind of defining the training loop as I showed on that one slide. And the training loop starts with the generator receiving a random seed, and that seed is used to produce an image. And basically from there, you can start to do your classification, the real versus fake stuff, and the loss from each is calculated, and the gradients are used to update both the generator and discriminator. And then going over here, this is kind of where you would display more data about your training, and then we can have this function for generating and saving images along training. And then we can call the train function, and then over a set amount of epochs, in this case 50, this is what the results look like from that. So you can kind of see maybe the first number is a 4, and the next one looks like a 5 or an 8, a 7, a 1, a 2, 9, and so on and so forth. But the point being is that this generator has learned to produce this output over 50 epochs, whereas it completely started from noise before. And so that is kind of the power of the generator there. And then we can kind of see the same thing again. And then here is I think the GIF in the end. This is what I showed at the beginning, but after training, these are essentially the results. So those are deep convolutional GANs. I would definitely recommend you to explore this notebook a bit more, like try this training in real time. I think I would have shown it here, but then we'd be here for a long time. So definitely recommend you to try it on your own. And here we kind of have a call to action, trying to generate facial features from like using GANs. I would also suggest looking at that. That data set is available on Kaggle. Definitely, I would urge you to come back to this notebook. And then I will continue with the presentation. that was kind of the overall, a quick overview of generative adversarial networks. I'm going to move on to stable diffusion. So stable diffusion might be like a newer concept to a lot of people, but essentially it is a text-to-image generative model. It uses text descriptions to generate images and image-to-image translations guided by text prompts. An important concept in stable diffusion is latent spacewalking. And this simply means sampling a point in latent space or kind of each of the state transitions and incrementally changing those latent representations. And you'll see what that means more in the coming slides. So I'll talk a little bit about the diffusion process. We're starting by taking an input image and we'll refer it to x sub 0. And then we're adding noise to it over a certain amount of steps, or in this case, capital T steps. And this process is known as the forward process or diffusion. And there's a neural network that will try to recover the original input image after all of that noise has been added. And that part is known as reverse diffusion or denoising. So let's talk about like the first part of it, which is forward diffusion. This is the part where we basically add noise. We're gonna take like some input image from that's a real data point and add noise to it. And then we also use Markov chains to do that noise injection process. And in that, each step only depends on the previous step. So at each of these steps in the chain, we're adding noise. And at the end of each of these steps in the chain, we have a new variable known as x sub t, in this case, a lowercase t. So yeah, we add noise at each of these steps, produce a new variable, and this is really apparent in the next diagram. Here's just basically the representation. We start off with this first picture of Golden Gate Bridge, and that is x sub 0. It's completely clear. There's no noise right there. And then at every step, we're kind of injecting this noise. And you can see it getting blurrier and blurrier until at x sub capital T, it is complete noise. And for notation purposes, I'll mention that the distribution Q represents the real data distribution. And then the second part of the process is known as reverse diffusion. We've so far coming back from forward diffusion, we've added a bunch of noise over T steps. But now the question is, how do we reverse it or denoise it? And as mentioned before, we're going to use a neural network to accomplish this. So we use it to approximate x sub t minus 1, or the step before, as we predict the parameters at each step. So this is diagrammatically what reverse diffusion would look like. Again, we're using that Markov chain, and we're going back step by step. And here, P sub theta represents the distribution of trying to recover that original image. And then I'm sure like a really pertinent question at the moment might be, so how does that model or that neural network recover information? The model recovers information by using the training data distribution to predict the visual details that would most likely be present given the input. So in this picture here on this slide, you can kind of see a low res image going to high res. And basically what the model is trying to do there at each of these blurrier points, you can kind of say like, oh, that's like noise being added to the image. So at each of those points, but what is the most likely pixel value to be present there? So that's a very broad overview of how that model tries to recover that information. And another question you might have is, I mentioned earlier that this Stable Diffusion is a text-to-image model. And so how does text even come into all of this? As I've only kind of talked about generating and recovering images so far. And text is added to this entire process of Stable Diffusion through a process known as conditioning. Conditioning consists of concatenating a vector representation of the text with a noise patch, and then training the model on the data set in terms of training it on image and caption pairs. And here to put it all together, like what is that Stable Diffusion model? It consists of 3 parts. The first part is a text encoder, which turns the text prompt into a latent vector. And then the next part is a diffusion model, which repeatedly denoises, say, in this case, the 64 by 64 latent image patch. And then finally, the final part of the model is the decoder. So it kind of turns that latent patch into a higher resolution image. In this case, also a larger image, as it's 512 by 512. And I'll show a diagram of kind of the model overall. So here's Stable Diffusion diagrammatically set out. First, you start with your text prompt, and it gets projected into a latent vector space by the text encoder. And then that text model is usually a pre-trained frozen language model that we use. And that prompt vector is concatenated to a randomly generated noise patch, which is repeatedly denoised by the decoder over a series of steps. The more steps you run, the clearer and kind of nicer, higher resolution image you'll get. I think we'll go over Stable Diffusion in KaraCV next, and the default value there is 50 steps, but you can change this hyperparameter to how you see fit. And then finally, after the step with the diffusion model, we go to the decoder, and then the 64 by 64 image in this case is sent through that decoder to properly render it into a higher res image. And with that being said, I will talk about Stable Diffusion with KaraCV so we can kind of see this process live. So there are several APIs available through KaraCV for Stable Diffusion, and I'll be kind of walking you through a couple of them. But before I get started, there are a few advantages of using KaraCV as opposed to other Stable Diffusion models out there. I think one of the other Stable Diffusion models out there is from Hugging Face, but we run like a kind of a comparison to it later. But before I get to that, I'll talk more about like the specific benefits of KaraCV, which is you get graph mode execution. You can also use XLA compilation. Just pass in that parameter as true for JIT compile. And then you also get support for mixed precision computation. And a couple things about KaraCV in general. This API is very easy to use. You can pull this off the shelf and use it for whatever your use cases are. And there are several performance benefits to it, which I will get to. But before I do that, I'll introduce real quickly kind of like how you would call this model. So you'd import the KaraCV library, and then from there within the library you have like Stable Diffusion, and kind of the 2 parameters you pass to begin with are the image width and height. And then I will talk more about that in a code lab, but before I get to that, now I'll talk about the performance benefits. So here are some of the performance results. So warm start, for people who aren't like familiar with that terminology, that refers to not having to instantiate the model every time you have to run it or use it. And so like, let's say in a production environment, you would only need to instantiate that model maybe once. And so that's a negligible cost to your computation. So here we kind of perform a comparison of KaraCV to the Stable Diffusion API from Hugging Face called diffusers. And as you can see, the runtime for KaraCV is a fraction of what it is with the Hugging Face API. But for complete like transparency, I'll also show like the results of the cold start. So cold starts means you have to instantiate the model every time you run it, which again isn't something you'd really do in a production environment. But we can take that into account to get like a full picture of how the KaraCV API works. Spinning up a new model instance is more costly in time, but as mentioned earlier, this isn't something you would have to do all the time. But with that being said, I think we can go ahead and actually walk through the code. So I'll give folks maybe like a minute to grab this URL, and then I'll switch over to the Stable Diffusion notebook. Okay, so I will switch over to the notebook now. So you should be able to see my the Stable Diffusion notebook I have pulled up. And for the sake of time, I will not be live running this again. I have already pre-run it for you in this presentation, just for to save time and make sure we're staying on track. But basically, what we're going to show here is how to generate novel images based on a text prompt using a KaraCV implementation of Stable Diffusion. So this is, you would essentially install TensorFlow and KaraCV to do this. And from there, you import them in. So it's only two quick calls to the libraries from TensorFlow and Keras. And I've shown this on a slide before, but this is how you would start constructing the model. So you have keras_cv.models.stable-diffusion, and then you pass in your desired image width and image height. I believe 512 and 512 might be the default values, but I would encourage you to check the API on keras.io to see what it says. And so from there, it's just this one line, and then we can go ahead and actually give it a text prompt. So moving to this example, we have model.text2image. So that's the function that you would call, and then the argument that you'd pass in is a photograph of an astronaut riding a horse. And then here's a quick function to kind of plot it and show what those results are. So these images that you see here, they're not photographed. They are completely brand new images that this model has created. And you can, what's interesting about each of these is you can kind of see the differences in each one, whether it's the color palette or kind of even the style of it. Each of these are unique and completely brand new images. But from there, you can actually give it a more complex prompt. So there's a lot of text in this next one, but again, we're using that text to image function. So we're passing in the prompt, cute magical flying dog, fantasy art, then golden color, high quality, highly detailed, elegant, sharp focus, and concept art, character concepts, digital painting, mystery, and adventure. And from there, again, you can kind of see how each of these three images are different from one another, again, in the color and composition, but they all hold those similar elements in being like akin to the texture of a digital painting, or they have those fantastical elements as denoted by fantasy art or mystery or adventure. Like this dog looks like it's going on an adventure. So there's that. And you could keep generating images like this. And you might be wondering again how this works. And I would encourage you to read through the documentation on this one too and explore this notebook a bit more. But it's like I've mentioned, the model, the neural network here will try to predict what those potential pixels are in that latent space. And you can kind of see like the Stable Diffusion model here in this GIF, like how you start with complete random noise and then ultimately you get some flowers at the end. And these all look like they were photographed, but they were generated from this model from complete noise. And then for review real quickly, here's the the model structure overall. We pass in the text, goes through the diffusion model, and then the decoder will produce that high-res image. And there's also the different Python files available. I would encourage you to go through those as well. And then, as I've explained, the perks of KaraCV, and here's perhaps another example. So these all kind of look like hand-done paintings. But the prompt that was passed in here is a cute otter in a rainbow whirlpool holding shells, comma, watercolor. So that's exactly kind of what you have here. You have 3 different representations of that. Standard model only took 8.66 seconds to produce this. And then, as I mentioned, you can also use mixed precision here. And we can go ahead and try, what are the results of both computationally and like what are the output images of that. And so the prompt here is cute, magical, flying dog, fantasy art, kind of like what you've seen before, actually. Golden color, high quality, highly detailed, elegant, sharp focus, concept art, character concepts, digital painting, mystery, adventure. So from here, you can see using the mixed precision model, you get it in 6.63 seconds, which beats the 8.66 seconds you saw before with fewer keywords passed in. So with more keywords, you also get these images quicker, and you can kind of see, again, these are all different dogs, or all different images, but they hold the same kind of concepts of digital painting and having those fantastical and mystery elements. And we can also use the XLA compilation. And this is what you get if you say an avocado armchair. This is the results of it. And so this is actually on standard without, I believe, XLA compilation. And then you can see it takes 34 seconds here. But then benchmarked with XLA compilation, we have the cute otter in a rainbow whirlpool holding shells watercolor. And using that, I was able to generate 3 images in under 7 seconds. And these are 3 unique and different images. So from there, if you kind of put it all together, here's just another example. Teddy bears conducting machine learning research. You get this as your prompt, or this as your result. And here is another example. A mysterious dark stranger visits the Great Pyramids of Egypt. This should be high quality, highly detailed, elegant, sharp focus, concept art, character concepts, digital painting. And you can see like you kind of get that here. These all have like that digital painting look and feel. And using XLA and mixed precision, I should point out, it only took under 5 seconds to produce. So here's basically a summary of the results. Starting with standard, it's around maybe 9 seconds rounded up. Mixed precision gives us, and XLA gives us about 6.5 seconds, while using both XLA and mixed precision gives us under 5 seconds. So I would encourage you to go back to this notebook and try to put in your own text prompts to see what you get and play around with the different types of runtimes that are available. But going back to the presentation, I think that's about all the content I had, so I'd like to open this up to Q&A now. Okay, I think the first question we have received is, what happens when you input an image of noise into the Stable Diffusion model itself? So you don't even start with a real image, you just go for noise directly. And the answer to that is the model would attempt to denoise that noise, and it would start kind of creating its own image, and it would continue to do this until it resulted in a increasingly clear, higher resolution picture. And that image would be completely artificial.
Okay, so there's another question here. Does running the model again with the same text prompt generate same output? So by instantiating the Stable Diffusion model in KaraCV, you have an option to provide model seed. So if you provide the same seed, you get the same output. And if you just let it do its default behavior, it chooses random seeds and you get different images every time you run the model. And there are a lot of questions on, can I add personalized pictures as part of training on the Stable Diffusion model? Can I add custom vocabulary? So this is something called textual inversion. So you can teach your model new concepts. A Keras tutorial for this is coming soon. So what you'd basically need is few pictures of your object and a special token that is not in your vocabulary that you would like to call this object by. And you construct an image caption data set, and then you fine tune your text encoder with your new data set, and then you can go and give prompts about your new custom object going forward with your model.
Yeah, and then the next question is this code available somewhere? Yes, and we have the links to both the deep convolutional GANs and the Stable Diffusion links. They're up on the TensorFlow and Keras websites, but we can also copy and paste the tiny URLs that were in this presentation in the main chat somewhere. But definitely look through the documentation that we already have available. If you just kind of search through the website for DC GANs or Stable Diffusion, you should be able to find it. And then someone asked, do you know any good resources for cycle GANs? And the answer is yes. There should be a TensorFlow cycle GAN tutorial to get started. Again, that's kind of, if you go on tensorflow.org and you look under the tutorials, you can find it there. And then regarding Stable Diffusion, does the noise function remain the same for each step during the diffusion stage? So I think this question is about in the Stable Diffusion model, maybe that second step. And yes, it is the same noise patch that gets repeatedly denoised at each step.
And there's a question on, is there an example of using KaraCV API to modify a previous image or mask the image and ask to fill the removed section or also to upfill an image? Yes, this is called in painting, and this function, this feature is available in KaraCV. You would need to provide the mask for an image and a mask which you want to remove from your image, and then a text prompt which you want what your mask to be replaced by what, and you can specify that using a text prompt. You can use that using Stable Diffusion.inPainting and give it a try.
And then someone asked, I really wanted to know how GANs are trained for different data because it is really hard to train GANs because of convergence issues. And so there are a number of GANs examples that use various data sets on keras.io. If you go to keras.io/examples/generative, I'd encourage you to start looking there and go from there. I was wondering if the meeting will be available to watch later on as a link or on YouTube. Yeah, so it says all sessions should be recorded and available after the event on the TensorFlow YouTube channel.
So thank you, everyone, and this was a great session. Thanks, Shilpa.
Thanks, Divya.